All right, welcome to this explainer. Let's just dive straight in, because today we aren't just looking at some dry textbook subject. We are going to unlock the invisible, ancient engine that literally powers our entire modern world, hydrocarbons. I'm going to guide you through this wild molecular universe, and honestly, by the end of this, you'll absolutely never look at your everyday surroundings the same way again.
I mean, seriously, what do ancient dead plants, the invisible gas that magically ripens your bananas, and the heavy-duty plastic pipes inside your walls possibly have in common? It sounds like a bizarre riddle, right? Well, they are all intimately linked by the exact same chemical building blocks. The decayed plants provide the raw material, and through the sheer magic of chemistry, we extract and transform them into the very molecules that ripen fruit and build our infrastructure. It's all hydrocarbons. So, here's our high-speed roadmap for today. We're going to hit the death of vitalism, explore carbon superpower, meet the AEF family, check out the aromatic ring, and finally wrap up on a massive scale with hacking fossils. Let's go.
Kicking things off with Section 1, the death of vitalism.
To really understand modern chemistry, we have to travel back to a time when scientists believed in, well, literal magic. Before the 19th century, early chemists sorted all compounds into two strict buckets: inorganic and organic. They firmly believed that organic compounds could only be created by a living plant or animal. They thought some mystical vital force was required to breathe life into these molecules. If you were just mixing things in a lab, there was absolutely no way you could make them. Then 1828 rolls around and boom, massive plot twist. Before this year, organic meant living things, period. But a German chemist named Friedrich Wöhler completely shattered this idea of vitalism. He took two strictly inorganic minerals, silver cyanate and ammonium chloride, applied a little heat, and synthesized urea, a fully organic compound created right there in his lab. The magic was officially dead. Post-1828, organic chemistry had to be entirely redefined, not by a magical life force, but simply as the chemistry of carbon.
Moving right along to Section 2, carbon's chain-making superpower.
Okay, so the word of the day here is catenation. It's the secret to life and modern industry, and it is carbon's ultimate superpower. It's basically the unique ability of carbon atoms to join together, forming short chains, incredibly long chains, and even rings. Imagine a limitless set of molecular Legos that can just keep snapping together to build structures of almost infinite complexity. That's catenation for you.
And the absolute key to all of this is the number 4. Why is carbon so absurdly good at playing Legos? Because it has exactly 4 valence electrons in its outer shell. This means a single carbon atom wants to form 4 bonds to be stable. It can form 4 single bonds with other atoms, or it can mix things up and form double or even triple bonds with itself. This insane flexibility is exactly what allows it to create the massive, diverse hydrocarbon structures we rely on every single day.
All right, Section 3, alkanes, alkenes, and alkynes. Let's meet the main characters.
Let's actually personify these guys for a second. We have the saturated hydrocarbons, like the alkanes. These guys contain only single bonds between their carbon atoms. Because every single carbon is fully saturated with hydrogen, they are the chill, highly stable ones. They really don't react very easily. But then we have the unsaturated hydrocarbons, like alkenes and alkynes. These have double or triple bonds. Because of those extra bonds, they are hyperactive, super reactive, and constantly looking for chemical trouble.
The naming system here is actually, well, it's brilliant. Just by changing a single letter in the suffix, you know exactly what molecule you're dealing with. If it ends in ane, like methane, it's an alkane with single bonds. Change that to ene, like ethene, and suddenly you have a double bond. Change it to yne, like ethine, and you've got a triple bond, making it the most reactive of the bunch. Literally one vowel shift changes the entire molecular structure.
Now, remember how I said alkanes were the chill ones? Well, they do react, but they mostly undergo what's called a substitution reaction, famously triggered by literal sunlight. It's a 3-step photochemical chain reaction. Step 1, chain initiation. Sunlight hits a halogen like chlorine and splits it into highly reactive free radicals. Step 2, chain propagation. That radical attacks the stable alkane, stealing a hydrogen and turning the alkane into a radical itself. Finally, step 3, chain termination. 2 radicals crash into each other, forming a neutral, stable molecule once again.
But what about those hyperactive alkenes and alkynes?
Because of those double and triple bonds, they don't substitute, they add. They eagerly break their extra bonds to grab onto new atoms in rapid-fire addition reactions. You can add hydrogen with a metal catalyst, add halogens, add acids, or even add water to make alcohol. But here's a real, wait, what, fact for you. Through polymerization, we take a gas like ethene, which plants naturally use to ripen your fruit, and we force those molecules to join together into massive chains called polyethylene. That is literally the plastic used to make the pipes in your home. From fruit ripener to plumbing, all from one single molecule. Mind-blowing, right?
Let's shift our focus to Section 4, benzene and the aromatic ring. So aromatic hydrocarbons are this really unique class characterized by a very specific functional group, the planar benzene ring. And yeah, in case you were wondering, they were historically named aromatic simply because early chemists noticed these compounds usually possessed a distinctly pleasant aroma or smell.
Now, looking at benzene, C6H6, you'd probably think its alternating double bonds would make it highly reactive, but it's actually the Lord of the Rings of chemistry. Because those double bonds alternate, they create what are called resonance structures. The electrons are essentially shared across the whole ring, making it incredibly tough and amazingly stable. Because it's so stable, its chief chemical reaction isn't addition. It absolutely refuses to break that ring easily, so it actually prefers substitution instead, just like our stable alkane friends.
Okay, Section 5, refining fossils into fuels. Time to zoom out.
Zooming all the way out to the planetary scale, where do we actually get all these invisible molecules? We mine them from the Earth as fossil fuels. We've got natural gas, which is mainly gaseous methane. Petroleum, that dark, sticky crude oil containing alkanes and alkenes, and solid coal, which is absolutely packed with those tough aromatic rings. And the absolutely crucial point to remember here is that these are literally the decayed bodies of ancient plants and animals that sank to the bottom of the ocean millions of years ago, crushed by time and pressure.
But here's the thing, crude oil straight out of the ground isn't actually very useful. The carbon chains are just too long. So we use a process called cracking. Think of a catalytic cracker like a giant molecular butcher shop. We are taking a giant, tough, kind of useless block of hydrocarbon meat, and using high heat and catalysts, we are chopping it up into smaller, high-value, incredibly useful cuts of petrol and gasoline.
So how do we sort all those chopped up bits? Through a process called fractional distillation, we separate petroleum based purely on the boiling points of the molecules. The smallest chains, carbons 1 through 4, boil off below 20 degrees Celsius to become bottled natural gases. Slightly larger chains become the gasoline for our cars. Even larger ones, boiling it up to 275 degrees, become kerosene for jet engines. And the really heavy massive chains become diesel fuel. We literally just boil the crude oil and it perfectly sorts itself by size. It's genius. And hey, we don't just crack liquid oil, we also hack solid coal through something called destructive distillation. By heating coal in the complete absence of air, a process called coking, we prevent it from just burning up into useless ash. Instead, it breaks down to produce incredibly pure carbon coke used for blast furnaces, alongside valuable aromatic coal tar and highly combustible gaseous fuels. So I want to leave you with this final thought. Take a second, right now, and just look around the room you are in. The synthetic fibers in your shoes, the plastic casing of your phone, the paint on your walls, the fuel that delivered your groceries. How many of those everyday items were forged in a catalytic cracker, totally re-engineered from the fossilized remains of life that decomposed millions and millions of years ago? Hydrocarbons aren't just chemistry on a chalkboard, you guys. They are the literal architecture of our modern existence. Thanks so much for joining me on this explainer, and stay curious.